Hey, welcome to this video on rates of change part 1. I'm glad you've made it. So let us begin with defining rates of change. Two things that we want to get straight with: instantaneous rate of change versus the average rate of change. So there are two different rates of change that we'll be talking about throughout this three-part video series. So let us begin with the average rate of change. Just imagine there is a function f of x given, looks like so, and then there are two distinct points on the graph, point P and point Q. So they are far apart, it's not really what we're going after, but they are distinct, so they are not identical. And now we will graph a line through point P and Q. So this blue line now, it's called secant line. And that secant line through point P and Q has a slope. So the slope, which is denoted with letter M, slope PQ, represents the average rate of change. So ARC. Now, the instantaneous rate of change. Imagine we have the same curve like just the one before, PQ, and now point Q is traveling very closely and eventually will collide with point Q. So point Q is getting closer and closer to point P, and eventually P is equal to Q. So every time the secant will be adjusted a little, and then eventually when point P and Q are become one same point, this line that makes a contact with the curve is now called a tangent line. Tangent line. So the slope of the tangent at point P represents the instantaneous rate of change. So the average rate of change, we're thinking about the slope of a secant, instantaneous rate of change, slope of a tangent line. Okay. So this example here illustrated on this side of the screen shows population of Canada between year 61 and 2006. And the objective here is to find how fast was the population growing in the year 2000. And why this is a very interesting example? Because we are working with a set of data, and please make note that the years in which the population was counted do not increase in steady sequence, right? And we are selecting a year which is not listed in this chart. So there is no year 2000, and yet we want to find how fast the population was growing in that year. So this is what makes that problem very interesting. So there's a couple different strategies that we'll use here. First one, finite differences. So what we do here, we find the difference in y values and see if that leads us to a conclusion that the data represented by these numbers can be fit into polynomial functions. So we did the first differences, the second differences, and then I also did the third differences, and there was no common differences that they were found in column with the third differences. Okay, so this is why we decided not to use this strategy, because there is no really 100% correlation with the given data. So that's one thing. And you may wonder, what is L1? What is L2? This is simply a screenshot from a graphing calculator TI-84 Plus. You don't have to have this particular calculator to work with this example. You don't have to have a calculator at all. It's just a easier way for us to represent the data on the screen. Okay, so finite differences strategy did not work, so that goes out the window. And then we will think of another strategy that can be possibly used to solve this problem. So the next couple of strategies that we will employ here is calculation of lines of the best fit, or curve of the best fit. So we did the cubic regression, quartic regression, and logarithmic regression. So yes, in order to employ these three different regressions, the graphing calculator was used. So this is what you see here on the screen. The cubic regression gave us a correlation factor which is equivalent to, if you can see that on the screen, about 99.86%. The quartic regression gave us a slightly better correlation, 99.91%. And then logarithmic regression gave us 99.89, almost 0.90%. So they all are very close. So this is one thing. The second thing, you see the graph down below that is represented by the curve of the best fit. So the cubic regression shows a steady growth and then levels off. The quartic starts turning back, so as if the population was decreasing, and the logarithmic curve is still growing pretty fast beyond that point, 2006. Now, should you be really concerned what happens past the point 2006? No, because this is not what we are trying to do here with this example. We want to find out what is the rate of change for the year 2000, which is before 2006. So arbitrarily made decision landed towards cubic function. There's no particular reason for why, but this is the option that we have here. So cubic regression function will be used to determine the possible rate of change, or the growth of population in Canada in the year 2000. Okay, so what you see on the screen right here is the following. This is the equation that represents the cubic regression. So you see terms to the power of 3, so the cubic term and the squared, linear, and the constant. So this is the choice that we have decided to go with, cubic function. And this is the list of coefficients A, B, C, and D, and this is the correlation factor, which is describing how close the points on the graph will fit into that cubic polynomial function. And again, just to recall, we are looking for year 2000 and there is no point on the graph in terms of the data that was provided. There will be a point where x is equal to 2000 on this curve of the best fit. So there will be that value, and this is why we need a function that defines the data in order to calculate a growth at that point that was not provided in the first place. So this is the reason why we do try to fit the curve and find a function that describes the trend in the data in order to do a calculation. Before we do the algebra ourselves, what I did here, I did find the tangent at point 2000. So this is the value of x, 2000.5. So the rate of change now is 279.47. So using a graphing technology, graphing calculator, so the rate of change is equivalent to 470 people per year in the year 2000. So according to this function, the cubic polynomial, the rate of change is about that. Now we will do the calculation using algebra and see whether we are close or exactly we end up with the same rate by using the algebra instead of the graphing calculator calculations. So let's do that. So the strategy that we will use here originate from the difference quotient. And the difference quotient, if you take a closer look, really does define the slope of a function, because f of x minus h and f of x represents two different values in the graph, and the denominator represents the difference between x values. So that reminds you of, or should remind you of, the following ratio, delta y over delta x, which is the ratio of a slope, right? So the difference in y values divided by the difference in x values. There's two intervals. There are two intervals that we are going to work with. The preceding interval, which is used for two sets of data. Since my objective is the year 2000, so I'm starting with 1999 and I will end with the year 2000. So this is the preceding interval. Then we will work with the following interval, which means since my objective is 2000, then I will find a point next to 2000, which is on the right-hand side, which is 2001. So we will define two different values of the slope with 99 and 2000 and 2000 and 2001. Okay. Since this is now set of x values and set of y values given the formula. So now we are working with this curve, with this cubic function. This was the curve of the best fit. So this is why we can extract x value that is equal to 2000, not from the chart. Look, just recall, the chart was jumping from 98 to 2001, and we couldn't do anything with it. The only rate that we can find based on the chart is the average rate of change, which is equivalent to 250,000 people between year 98 and 2001. But this is not what we want to find. We wanted to find how fast is the population in Canada in this very year 2000. Okay, so this is where that calculation comes from. Okay, the year 99, the year 2000, and the ratio gives us 284. Then we use the following interval, the year 2000 minus 2001 minus 2000 divided by 1, which is missing for whatever reason. So this is divided by 1. Okay. And now I have to fix what I accidentally deleted. So this is 279. Okay. So now we found the preceding interval ratio, and for the following interval ratio we have found the value, and this is of course positive. So the next step you do, find the average. Find the average. By using preceding interval, following interval. So you add this together, divide by 2, and now you get the new value. So this is 281.5. If you use your calculator, you get that reading, which means the following. The population here in the column Y is given in thousands. So let's change this value to 281,500. So this is the rate of change, the estimated rate of change of the population of Canada in year 2000. So the population of Canada was increasing by about 281,500 people, and this is very close to the calculation that we have obtained using graphing calculator. Okay, so you're not going to always be able to use a graphing calculator, and therefore in this case, if you were to not use technology at all, we could only make the conclusion what was the average rate of change between 98 and 2001, since the data for 2000 was not provided. So it would be just that strategy, no technology estimated between year 98 to 2001. If there is a possibility of use a graphing calculator or any graphing software that allows you to generate the curve of the best fit, yes, you can do that with graphing calculator, either Texas Instrument or Casio, any other software available nowadays in the market. So 2000 point was available because of the curve of the best fit, and you do preceding interval, following interval, find the average, and this is your estimated rate of change. Thank you very much for watching this video. I hope that served you in finding out how to find the instantaneous rate of change, how to create the numbers from the curve of the best fit. Part 2 and 3 of this video will have very different application. So I see you next time. Thank you very much. Bye for now.